So welcome back. Today we will be looking at integrals that might seem impossible to solve at first because there's no obvious derivative to use for the U-substitution. The trick? We don't integrate yet. We will be applying algebra first. In particular, we will be using tools such as long division, splitting the fraction, and completing the square. Let us start with this level 1 problem. So for this first problem, our goal is to find the antiderivative of x squared all over x squared plus 1 dx. There's a typo here. I believe there's a typo here. So bad start. First problem, typo already. This one. Okay, so let's repeat. So this is the antiderivative of x squared all over x plus 1 dx. So in here, of course, the first thing to do is to try to apply U-substitution. So for instance, if we let u supposed to be x plus 1, which is like the natural choice, then we'll get du to be equal to dx. Now you might get an answer here if like you'll replace this by u, and then for the numerator you will be like from here you can write x equal to u minus 1. But as you can see, that is kind of quite a lot of steps. So I don't think that is the best route out here. You might think to let u to be equal to x squared. If you do that, du will be equal to 2, oops, there's an x here, 2x dx. This seems fine, but we won't be able to have a solution for this denominator. So for these types of problem wherein the numerator, the degree of the numerator is higher compared to the one on the denominator, a trick that you could use is to apply long division or synthetic division. For this one, I would be applying a long division since it's more general and applicable to different types of rational functions with different degrees out here and here. So let's do that one. So applying long division, so we'll have here the divisor x plus 1, and then here goes the dividend. So we'll have here x squared. In long division, the tip here is that if there are missing variables of lower degrees here, like so this one is x squared, x is missing and the constant part is missing, what we do is we just add plus 0x and plus 0 out here. So, oops. So this one is like the placeholder for the degree 1 variable, and this one is the placeholder for the constant variable. Okay. So once we have this, we just solve this one like usual division. So we'll have your x, since we need to multiply x so that this one becomes x squared. So we'll have your x squared plus x. We subtract these two. Subtracting these two, this will cancel out and we will be left with negative x. Then let's just put plus 0 here. And since this one still has the same degree as this one, we can still divide. This time we will have minus 1, so that we will have here negative x minus 1. We subtract these two, subtracting this will cancel out and we will be left with 1. So here, this will serve as, again, this is our divisor, this one is our quotient, and this is our remainder. By long division, this just means that our integral, or our integrand rather, out here simplifies to first the quotient x minus 1 plus the the remainder out here all over the divisor. There. So this is the simplified form of our given. Once we have this one now is much easier to anti-differentiate. Let's put it here. So the x out here, this x just becomes simply x squared over 2 by the power rule of anti-differentiation. Minus 1 out here just becomes minus x. And then this one, take note that technically we'll be applying a U-substitution there, u equal to x plus 1, to obtain ln of x plus 1. For ln, we usually skip this substitution out here if it's quite obvious. This is the answer for our problem. So as you can see, we didn't need some complicated substitution out here. All we needed is to apply the long division, an algebra trick. So let me just readjust this one and this one. There you go. That's it for our level 1 problem. It's quite straightforward. Just to summarize it or just highlight the key thing here. If you have a rational expression wherein the degree of the numerator is higher than the denominator, you can apply long division. It's quite a handy trick. Let's proceed to the next one. Let's just go here. For this next one, we'll have the following. Okay, for this next one, our goal is to anti-differentiate this integrand x plus 1 all over quantity x squared plus 1. Okay, so to do this, clearly we can't use the trick that we used in level 1 of long division, since the degree of the denominator is much higher than the numerator. So we'll try to substitute here. So let's try to let u be equal to, the most natural substitution here is probably the denominator x squared plus 1, because when you differentiate that one, you'll lower the degree, and we might hope to cancel this one out. So let u be equal to x squared plus 1. If u is equal to x squared plus 1, du is equal to 2x dx. There. The problem here is that our du here, hopefully it becomes the numerator. But in our case, we have the numerator to be x plus 1 and this one to be 2x dx, or maybe we can adjust it to become x dx. So it seems that this won't work, but a trick here is to split this antiderivative, or this integral. What I mean by that is we can express this as two integrals wherein we will force x dx to come out. How do we do that? Take note that in rational expressions, or basically fractions, if we have a plus b over c, we can write this as a over c plus b over c. So in our case, what we can do is we can split this as x over x squared plus 1, and then 1 over x squared plus 1. Okay, let's just fix this one. I think it's consuming, oh no, there. It's consuming quite some space. Okay, so yeah, so just watch my adjustment process out here. Let's make it neat. There you go. So just move this out here. There. So once we have this, take note that for this one, we can rewrite this as, let's just put it out here. Oh, what's this? Should be this. We can rewrite this as, if we divide 2 both sides, we will have du over 2 equal to x dx. Why did we do that? This thing here now perfectly matches this part out here. So we will have this one. For this first integral, this one just simplifies to 1 over 2 integral of 1, then here is u. Okay, let me write this better. This becomes 1 over u du. And then let's just copy this other one. It's nice. From there, we know the antiderivative of that one. That just simply becomes 1 over 2 ln of absolute value of u. The absolute value here is, you can remove it if you want. I don't know, but I'm not really particular with it. It's fine with me if it's just parentheses, but I'm sticking to the formula that I know. And then for this one, take note that this is just simply arctan or tangent inverse of x. Okay, so take note of that one. This is a known formula. Basically, if you know the derivative of tan inverse, it's just this one. Good. Then once you have this, again, when we start with x, we need to end with x. So we just replace the u here with the corresponding x. So this simplifies to 1 over 2 ln of x squared plus 1 plus tangent inverse of x plus c. This is the answer for this problem. Okay, so that's pretty nice. The key here again is to split. Okay, so let's just rearrange this one. Let's maybe put it out here. This one out here. Yeah, I think that's okay. Let's move this quite out here, and then maybe this one. Good. There. So that answers this second problem. So we have this and this. Okay, now we move on to the third one. So let's have this third one. Okay, so we have here the antiderivative of, oops, not yet. This is for the fourth one. 1 over x squared minus 6x plus 13. dx. There. Now for this one, you might think of using the, obviously the level 1 trick that we use won't work, since again the degree of the numerator is lower than the denominator. Let's just write this properly. This one is 6. This one is 13. Moreover, we we can't really split anything out here since this one is just 1. So it's just boring to split. It will become 1/2 over 1. You might think of using U-substitution immediately, letting U to be equal to x squared minus 6x plus 13, but this would lead to a du that contains x. X is not in the numerator, so that won't really work. What do? The trick here is that you can apply completing the square out here. By applying completing the square in the denominator, you would reduce it to the form wherein if you apply U-substitution, it would only have a derivative of a constant. Okay, so let's do that one. So let me use a different color just for a different vibe, I guess. So let's put it out here. So note that x squared minus 6x plus 13. By completing the square, tells us that if you have a quadratic, let's say, expression out here, ax squared plus bx plus c, wherein a here is positive, then if you add and subtract here b squared over 4a, then you could eventually convert this thing out here into a perfect square trinomial. Okay, so I hope you were able to catch that one down. So in this case, if this one is our quadratic expression, b squared over 4a here would become negative 6 squared all over 4 times 1. This simplifies to 36 over 4, and this one is just 9. So that's what we add and subtract, and look at this one. So for x squared minus 6x, let me add and subtract in between out here. So that we have plus 9 and minus 9 plus 13. Okay, once you have this one, take note that if we adjust this quite a little here and we group this first part together, this thing here is now a perfect square trinomial. What's special about perfect square trinomial? Well, it factors into a square of a binomial. In particular, for this one, this factors into x minus 3 squared. Then it's going to be plus 4. Okay, so the 4 came from the combination of these two. Why is it x minus 3 squared? Basically, when you convert a perfect square trinomial to a square of a binomial, you get the square root of this, you get the square root of this, you copy this sign out here. So let's rewrite the given using this one. So this thing out here, we can rewrite it as, let's move this a little bit lower. There, we can rewrite this as x minus 3 squared plus 4. Here's 1, here's dx. There, then observe, we can now kind of apply U-substitution. Okay, so I'm out of colors, let me use red. So if we let u equal to x minus 3, then du is simply just dx. Okay. So once we have this one just simplifies to 1 over du out here. I have u squared plus, I can write 4 as 2 squared. So once we have this, just recall that okay, let me just take note of it. So recall out here that the integral of du all over u squared plus a squared, wherein u here is a variable and a here is some constant, is just equal to 1 over a tangent inverse u over a plus c. Okay, so this is a known formula in like calculus. So we can apply this formula in our in what we have. Okay, so I'll let go of this one. Make sure that you have taken note of this. Yeah. So I hope you were able to take note of that one. Applying this to what we have, this just simplifies to 1 over 2 tangent inverse. Write that one properly. Tangent inverse of u over 2 plus c. Then again, we started with x, we must end with x. Using this relationship out here, we can just rewrite this as 1 over 2 tangent inverse of x minus 3 all over 2. This is the answer for this problem. Yeah, so as you can see, this one is kind of tricky, but once you get used to it, it becomes easy. So let me just readjust this here. Yeah, to keep it neat. Whew. Okay, so that's the third level. Let's go on the fourth level. So level 4. For level 4, we have 1 over square root of 3 minus 2x minus x squared dx. Okay. So for this one, the trick is actually the same as level 3. We will apply completing the square out here. But this time, take note that this one, recall that earlier I mentioned that when you apply completing the square to some quadratic expression, a here must be positive. But in this case, a here is not negative. So how do we deal with that one? It's actually pretty simple. So again, completing the square. So we start with 3 minus 2x minus x squared. If we want to apply the completing the square, again, with the coefficient of this squared term must be positive. Simple trick to do that one is just to factor out the negative one. So we'll have a negative of x squared plus 2x minus 3. Then applying completing the square, if this is our expression, we just take b squared over 4a, and this equates that is 2 squared all over 4 times 1, which just simplifies to 4 over 4 or 1. So that is what we add and subtract out here. So we have negative of x squared plus 2x plus 1, right? Minus 1 minus 3 here. And this just simplifies to this thing now again is a perfect square trinomial. Converting it to its square of a binomial, it just becomes x plus 1 squared minus 4, and then plugging in back the negative, we will obtain 4 minus x plus 1 squared. So that is the completing the square version of this denominator, the one on the inside the radical. So this thing here, like earlier, we can rewrite it as follows. So we'll have here this integral of 1 over the square root of 4 minus x plus 1 squared dx. And then like earlier, we can now apply U-substitution here easily. So we can let u be equal to x plus 1, so that du becomes dx. Applying this substitution, we will obtain here 1 over the square root of, again like earlier, I'll write 4 as 2 squared. Then this is u squared du. Whew. And then from here, again, this is a known formula. Oops, it's was a known formula in calculus that, so let me just put here, recall that if you have the integral of du all over the square root of a squared minus u squared, yeah, that one, this one is just equal to sine inverse of u over a plus c. There, this matches perfectly to what we have. Just take note that unlike earlier, there is no 1 over a out here. So careful of that one. And so applying that formula, this just yields to sine inverse of u over 2 plus c. But then again, we must end with x. So we just apply this conversion out here, that relationship. We will end with the sine, the arcsine or the sine inverse of x plus 1 all over 2. So that is the answer for this problem. Good, pretty good. So that's the answer for this fourth item. And finally, we can finally have our last item for this. I think this video is quite long, but yeah, I'm trying to explain everything in detail, so I guess that's the reason it's quite long. Let's move in this fifth one. Also, kindly comment down below if you like this no editing video. I mean, I guess it makes the video more, I don't know, more direct and more realistic, more relatable, I guess, because I also make mistakes. There, so we have here the integral of this rational expression 2x plus 3 all over x squared plus 2x plus 5. This item is a combination of everything that we have. So observe that the degree of the denominator is higher than the numerator. Earlier, what we did here is we split. We will do that again this time. And then also observe that once we split, we will actually be able to apply completing square, since we'll obtain from the split a constant over this ugly quadratic out here, which we can complete the square later. Good? Whew. So let us proceed. So again, we start by letting u be equal to the denominator, so that we can determine what form of split we will do out here. If we let u to be that one, du would become 2x plus 2 dx. So for our numerator is 2x plus 3, so we will adjust accordingly with the right. So this one becomes, we can split it as 2x plus 2 out here, x squared plus 2x plus 5 dx, plus from 2x plus 3, if we subtracted 2x plus 2, this will just become 1 of x squared plus 2x plus 5 dx. There. So just to keep our solutions neat, let me name this one as, I would say, A, and this one as, let's name this as P, and let's name this as I to represent pi. And let's deal with these two individually. So for P, note that we can apply the substitution that we have out here. So applying that substitution, then this one out here, just simplifies to the integral of 1 over u du. Okay, you got that one down. So this one becomes du, this one becomes u. And so we'll have here ln of the absolute value of u plus c but ln of absolute value of u. Oops, let's just put it. Again, we go back to x. U is just this one. So we'll just have here ln of x squared plus 2x plus 5 plus c. So that goes for p. We proceed with, let's just move this out here. We next proceed to I. So I hope you got that one down. It's kind of similar to what we've been doing so far. For I, we'll deal with this. Okay, let me copy it later. We'll this with this thing out here. Again, since this one we have a form of constant all over this quadratic out here, we will be applying completing the square. So applying completing the square, let me just use white. Note that x squared plus 2x plus 5, applying completing the square would yield x plus 1 squared plus 4. So I skipped that one down, but I hope by this time you're kind of comfortable with it already. Okay, so take note of that one. That is, it's completing the square form. You can verify it. And so this thing here, oops, this thing here would just be equal to the integral of 1 over x plus 1 squared plus 4 dx, and then like earlier we will be applying U-substitution out here. So we have used u already here, so let me just use v. So let v this time be equal to x plus 1, then dv will just be equal to dx, and so we can rewrite this given as the integral of 1 over v squared plus, let me write 4 as 2 squared. And I hope you remember this form earlier. This is exactly what we had earlier. Let me scroll that one up. This form. Exactly this form. So it would become just like this. So this one just simplifies to 1 over 2 tangent inverse of v over 2 plus c. Okay, good. Then again, we started with x, we must end with x. We use this relationship out here. So this one will just become 1/2 of tangent inverse of x plus 1 all over 2. Okay, so that is the answer for this. Oops, that's not yet the answer for this problem. I mean, at least in particular for this one. But again, our goal is to find p plus I, this expression out here. Okay, so therefore, we just add what we obtained. Okay, so it's over here. So we can conclude that, so this one here, oops, that's a different problem, my bad. This one out here, oops, there, is just equal to p, the one we obtained in p, just this one. Okay, I can disregard c. C is just a constant. Let me just put it at the end here. Plus this one out here, and then just add a plus c at the end. This is the answer for this last item. Whew, that's a culmination of everything that we had so far. Okay, so yeah, so that's it. This is the full list. Let me rearrange it. So let me maybe we can move 3 out here. There, there's 3 and 4 out there, and then 5 here in the last one. Yeah, so that's these are, so maybe you can see it more visibly if we remove this there. So this is the list of all the items that we had for this video. To summarize, we use algebra tricks such as long division, completing the square, and a certain splitting of a fraction to solve these integrals or these antiderivatives. Yeah, so I hope you enjoyed that one. You can check the link in the description down below. I will be uploading a PDF version of everything that we have here for your own review. And yeah, good luck on your future endeavor. That's it. Thanks.